This video is going to be about work and power and how are those things related. Or stretch some springs, maybe race a car around. Here's a motor spinning around, and here's a walrus. I'm not really sure why the walrus is here, but anyways, there we go. We'll start off with some basic definitions first, and then we'll get into some examples. Here's the basic definition for work. Work is change in energy. So how do you change something's energy? There are a couple basic ways we could do this. One way is we could lift something and take an object that has a mass and lift it up, and you've changed the energy of this object. So you've done work on the object. You could stretch a spring, grab onto the spring and stretch it. So you have increased the energy in the spring by doing work on the spring. You could also change your velocity. So you have a car that's not moving and then it starts moving, or a car that's at one speed and speeds up. Generally, when we're talking about changing velocities, we want to increase the velocity to do work. Although you can also decrease the velocity of a car by doing work. If we're changing energy, each one of these represents a different type of energy that we'll be talking about in our class. This particular energy, when you're lifting something up, is going to be gravitational potential energy, GPE. So you want to change the gravitational potential energy. This type of energy in stretching a spring is going to be called elastic potential energy, stretching a spring. And when you change something's velocity, you're changing the kinetic energy. That's the energy of motion. There's formulas that go with these that are pretty basic. For gravitational potential energy, the formula is mass times gravity times height. So if you want to change something's gravitational potential energy, you could, it's hard to change something's mass. It's pretty hard to change g. So what you need to do is you need to change the height of something. So this is the height that you've lifted it. And if you lift it up a particular height, then you've changed its gravitational potential energy. And we say that that takes work to do that. As far as elastic potential energy goes, elastic potential energy, the formula is 1/2 times k times x squared. X is the distance that you've stretched the spring. So here's x right here. How far did you stretch the spring? And this value k right here, we'll talk more about in class later, but it's called a spring constant. And you would have to be given this value or perhaps figure it out for any particular spring. The basic idea is that some springs are actually really stiff and they're hard to stretch, and then some springs are a little easier to stretch, so they stretch more easily. And the spring constant tells you how easy is it or how hard is it to stretch the spring. A higher k value means a higher spring constant. Like I said, we'll talk more in class about that. But you can do work by stretching a spring. I have to do force and pull like this, and I have to stretch the spring. And now we say the spring has elastic potential energy, can let go of the spring and release the energy. Kinetic energy also has a formula. That is 1/2 times mass times velocity squared. So if you want to change something's kinetic energy, once again, it's hard to change mass, so you can change the velocity. You could speed something up or slow something down by changing the velocity. So work is change in energy. Because it's change in energy, the units here are all going to have to line up with energy. So let's talk about units. Go to a new page right here. Let's talk about units for energy and subsequently also for work. The units for energy, some potential units for energy that you've heard of before, we have calories and joules are main units for energy. There's other types of units for energy as well. Calories works really well in chemistry for particular reasons, but joules tends to work better in physics. Now, of course, they're interchangeable, and you can use joules in chemistry and you can use calories in physics depending on what you're doing, but we're going to stick with joules. That's going to be our unit of energy. 1 joule has something buried inside of it. 1 joule is actually a kilogram times a meter squared divided by a second squared. That's what's buried inside of 1 joule. So let's do an example of a joule that I think might help. let's talk about gravitational potential energy. That's mgh. We'll start off with a ball on the ground here, and let's make the mass of the ball be 1 kilogram. And I want to lift the ball up to a certain height, and I want to figure out how much energy it has at this particular height, how much gravitational potential energy it has at that height. So let's, well, of course we know g is 9.8, so let's say that we lift up the ball a distance of 0.1 meters. So that's 10 centimeters. So I've lifted a ball up to a height of 0.1 meters. Now I can figure out how much gravitational potential energy it has. GPE is m times g times h. The mass was 1 kilogram. Of course, g, 9.8, but we can just as well call it 10, and that's meters per second squared for g. And then my height over here is 0.1 meters. So of course you see what I did here. I chose those numbers on purpose. So this is all going to equal 1 kilogram meter squared divided by second squared. And better off to call that 1 joule. So the gravitational potential energy of the ball up there is equal to 1 joule. It also happens to be equal to the work necessary to lift up the ball. So if there's a person here and they've lifted up the ball from the ground and they've lifted up this height, we say that they have done 1 joule of work in lifting the ball. And that's also how much energy the ball has when it's up at this particular height, right? Okay, let's do a spring problem just for fun. So let's say that we have a spring right here. It could be either of these springs. And I'm just going to tell you what the K value is for this spring right here. The K value for this spring is, let's call it 10. And the K values, the units for K values are newtons per meter. That's how we evaluate the K value. And let's say we're going to stretch this spring out. And let's do, well, let's just make it really easy. We'll say we're going to stretch it out 1 meter. I'm not going to come out with 1 joule for this one. And I want to figure out how much elastic potential energy does the spring have when you've stretched it out. That's 1/2 times K times x squared. And x is how far we've stretched it. So let's figure this out right here. So we have 1/2. My K value is 10, and that's just going to be given. Remember, any spring has its own K value depending on how stretchy it is or not stretchy. So we'll plug that in. 10 newtons per meter times my distance, x, was 1 meter, and we'll square that. This is going to be pretty easy math to do. We're going to come out 1 squared is 1. That's why I chose that number. So this is going to turn out to be 5. Now look what happens to the units right here. That's going to be meters squared, and that's going to be one of the meters is going to cancel here. So that's newtons times meters. That's pretty strange though, because the units for energy that we had before on this page were kilograms meters squared per second squared, and we call that a joule. Remember though, buried inside of a newton is actually a kilogram meter per second squared. That comes from F equals ma, if you want to review that. Force is mass times acceleration. So it does turn out that this newtons times meters is actually another way just to say joules. So that's 5 joules, just like that. If there were a person up here and this person were stretching the spring, if this person took the spring and they stretched it, so they grabbed onto it like this and they stretched it, they gave energy to the spring. They increased the energy inside the spring, which means that they did work. And work is change in energy. Work is change in energy. Great. Let's do one other example. Let's do a car example. All right. So let's say we've got a car and we're going to increase the velocity of the car. So there's my car. Let's make the car have a mass of, I don't know, let's make it a little unreasonable, 100 kilogram car. And it's going to start off with 0 speed here, and then as it gets going over here, we'll say that it has a speed of, let's say, just to make the numbers really easy, we'll say it's 10 meters per second. And I want to figure out how much kinetic energy does the car have after we've sped it up. Kinetic energy is 1/2 m times v squared. That's 1/2 times 100 kilograms times 10 meters per second squared. So that's 100, that's 100. So 100 times 100 is going to give me 10,000, and half of that is going to give me 5,000. And the units are going to work out kilograms meters squared divided by second squared. And that's the same thing as 5,000 joules, or just 5,000 J for joules. Same thing here. Something had to do work in order to make the car speed up. This time it wasn't necessarily a person that did it, but there's some sort of engine or some sort of motor inside the car, and that motor did work in order to increase the speed of the car from 0 to 10 meters per second. So there's work being done here. Anytime you have a change in energy, there's going to be work being done. Work is change in energy. Right? So the change in energy was 5,000 joules, so there was 5,000 joules of work done on the car. Okay, let's move on and let's talk about power a little bit, and then we can do some practice problems with power. Sometimes we want to know how quickly something can do some work. All right, so we're going to define power as work divided by time. Work over time. Can you change something's energy? Change in energy. And how much time did it take you to change that energy? So work is energy, change in energy divided by time. Let's do another example here. Let's say we have a person and they lift a bowling ball, and this time let's do the weight of the bowling ball. Let's do the weight of the bowling ball. Let's say the weight of this bowling ball is, 20 newtons. That's the weight of the bowling ball. They're going to lift the bowling ball up 1 meter in height, and then the time it takes them to do that is going to be, well, let's say it's 5 seconds. Well, that's pretty slow. 20 newtons is not very heavy, so this is a pretty slow lift. And I want to calculate the power output here. So in order to calculate the power, I need work, time, change in energy, and time. For this particular case, the change in energy is going to be a gravitational potential energy. So one way we could solve this, if I want to figure out the change in energy, is I can figure out the change in gravitational potential energy of the bowling ball. But there's another way that we can actually figure out work. There's another equation for work. Work can also be expressed as a force times a distance. How much force was exerted and for how much distance was that force exerted over? In this particular case, 20 newtons was the force and the distance was 1 meter. So we can figure out very easily how much work was done here. 20 newtons times 1 meter. That gets me 20. Remember, newtons times meters is the same thing as joules. So the energy here was 20 joules. And now if I want to figure out the power, that can be work over time or change in energy over time. Work over time. And in this particular case, that's 20 joules divided by 5 seconds. And that gets me 4 joules per second. Joules per second is actually the same thing as watts. It's a rate. It's a rate of how much energy you're going to use per time. Energy per time is a rate. Units up here, we use joules for energy, and we use seconds for time. So joules per second, and this is the same thing as a watt. So that's our formula for power. And you can calculate the power of different things. You could calculate the power of a car and speeding it up, if your change in energy was kinetic energy, you could see how much power it would take to, say, stretch a spring out like this, right? You could see how much power it takes to lift up a weight to a certain height in a certain amount of time. Of course, we can express our power in watts. Another way we were expressing power in class was in horsepower, and 1 horsepower is equivalent to 746 watts. And we explored that in class as well. Hopefully this video has helped you figure out our units for energy, different types of energy, kinetic energy, elastic potential energy, gravitational potential energy, and just what work is in general. See you later, Walrus.